In June 2025, Meta and Constellation signed a 20-year agreement for the full output of the Clinton nuclear plant in Illinois, 1,121 megawatts, beginning in 2027. The public announcement does not tell us the price, but it does tell us the product: clean, firm electricity with a long-duration buyer. 2 years earlier, another Constellation nuclear plant in New York started making hydrogen. 9 Mile Point installed a 1.25 megawatt electrolyser. The hydrogen does not go into a pipeline or an export terminal. It goes into the nuclear plant's own cooling system. Put those two receipts beside each other. One clean reactor megawatt-hour can go to the grid and a data center buyer. Or in a simple low-temperature electrolyser, it can make roughly 20 kilograms of hydrogen. Which buyer should get it? That is the nuclear hydrogen decision, not whether the molecule can be made. It can, not whether nuclear electricity is low carbon. It is. The question is whether hydrogen creates more durable value than the best electricity check available to the same reactor. My answer is split. Existing nuclear plus a captive hydrogen customer can be a real bet. A new reactor built around merchant hydrogen is a completely different project, and today it usually loses unless a firm hydrogen contract, useful process heat, and policy support create a premium over selling the power. An advanced high-temperature nuclear hydrogen? Promising physics? Not yet a bankable commercial project class. People often call this pink hydrogen, as if one color describes one set of economics. It does not. There are at least 4 different decisions hiding under the label. Case 1 is an existing light water reactor feeding a conventional electrolyzer for hydrogen used inside the fence or next door. That is the strongest case. Case 2 is a new small modular reactor feeding a conventional electrolyser beside an industrial customer. That stacks a new reactor, a new hydrogen plant, and a new product contract. Case 3 is an advanced high-temperature reactor feeding solid-oxide electrolysis with both electricity and heat. That is the efficiency story people get excited about. Case 4 is the option most hydrogen presentations leave out: do not make hydrogen. Sell the clean, firm electricity. That 4th case is not failure, it is the control. Throughout this episode, I will say small modular reactor rather than use the letters SMR. In hydrogen, those same letters usually mean steam methane reforming. One acronym should not get to hide 2 completely different carbon and capital stacks. The decision rule is simple enough to put in one cell. Calculate the hydrogen netback created by one reactor megawatt-hour. Subtract the best electricity value for that same megawatt-hour. If the answer is negative, sell the power. If it is positive, then, and only then, start underwriting all the ways the integrated project can still go wrong. 9 Mile Point is the operating receipt, and its narrowness is exactly why it matters. The U.S. Department of Energy says hydrogen production began in 2023 with a 1.25 megawatt low-temperature electrolyser. The plant uses the hydrogen in its cooling system. Before this project, that hydrogen was delivered from an outside supplier and produced from fossil fuel. A DOE project review estimated the plant could avoid more than $800,000 per year of external hydrogen purchases. This configuration removes several problems at once. The nuclear plant already exists. The grid connection already exists. The electrolyser can run at a high utilization rate. The hydrogen buyer is the same operator. The product moves across the site instead of across a continent. And the commercial comparison is not just wholesale electricity. It is the delivered cost, logistics, and reliability of trucked-in industrial hydrogen. That is a very good niche. But notice what the project does not prove. It does not disclose a merchant hydrogen sale price. It does not build a regional pipeline. It does not finance a new reactor. And a 1.25 megawatt electrolyser beside the large existing nuclear station does not prove that a 100 megawatt hydrogen plant can find a buyer. The wrong lesson is nuclear hydrogen is commercial. The right lesson is more useful. The first bankable nuclear hydrogen project may replace a delivery truck, not create a new commodity hub. The standard argument for nuclear hydrogen starts with capacity factor. A reactor can run day and night, so the electrolyser can run more hours. More operating hours spread the electrolyser's capital cost across more kilograms. That is true and incomplete. Every hour the electrolyser runs, it also consumes electricity that the reactor could sell. High utilization improves the hydrogen equipment and raises the amount of electricity being diverted. The capacity factor advantage and the opportunity cost grow together. You will sometimes hear that hydrogen should use only surplus nuclear. Fine, Show me the hourly price curve, the capacity obligation, the transmission constraint, and the contract the reactor is allowed to interrupt. Surplus is not a permanent fuel source. It is a market condition with a timestamp. This is why the unit in our calculator is not only dollars per kilogram, it is dollars per reactor megawatt-hour. For every megawatt-hour sent to hydrogen, the model asks 4 questions. How many kilograms come out? What is each contracted kilogram actually worth? What conversion, capital, heat, and delivery costs sit between the reactor and the customer? And what electricity check did the operator turn down? That makes nuclear hydrogen an allocation problem before it becomes a color story. Start with conventional low-temperature electrolysis. A historical NREL and national laboratory model used 50.2 kilowatt-hours of electricity per kilogram of hydrogen. Divide 1,000 kilowatt-hours by 50.2, and 1 electrical megawatt-hour makes about 19.9 kilograms of hydrogen. That is a model input, not a universal plant guarantee. Compression, storage, delivery, auxiliary loads, and degradation sit outside that clean division. High-temperature electrolysis changes the energy split. Solid-oxide cells receive steam at roughly 700 to 800 degrees Celsius. Heat supplies part of the energy required to split water, so the process needs less electricity. In the same historical comparison, high-temperature electrolysis used 35.1 kilowatt-hours of electricity plus 11.15 kilowatt-hours of heat per kilogram. 1 electrical megawatt-hour therefore supports about 28.5 kilograms of hydrogen, but it also draws about 0.32 megawatt-hours of thermal energy. That is a real physics advantage. It is not free energy. Extraction steam can reduce turbine output. The heat exchanger, steam loop, controls and safety case add equipment and integration work. The electrolyzer must survive high-temperature cycling and degradation. The reactor and hydrogen plant also have to agree about which asset follows the grid. DOE's public technical table reports 34 kilowatt-hours per kilogram as a high-temperature status and target value, alongside separate degradation and lifetime targets. Treat that as a technology target table, not a receipt from a commercial integrated nuclear hydrogen plant. This distinction, operating, demonstration, model, or target, will save you from most of the misleading charts in this sector. DOE originally described 3 U.S. nuclear hydrogen demonstrations. 9 Mile Point was the low-temperature operating case. Davis-Besse in Ohio had a published hydrogen production target of 2025. Prairie Island in Minnesota had a published 2026 target for a first-of-a-kind high-temperature demonstration. The latest DOE status source I located is a 2024 program presentation. It shows 9 Mile Point producing, it shows Davis-Besse working through electrical and switchgear scale-up, and it shows Prairie Island as a 150 kilowatt high-temperature system tied into the plant's thermal line. I did not find a newer primary commissioning notice for Davis-Besse or Prairie Island in this research refresh. But Davis-Besse now has a competing receipt. In January 2026, owner Vistra signed 20-year power purchase agreements with Meta covering Davis-Besse and other nuclear sites, with purchases beginning in late 2026. The agreement keeps the electricity on the grid, and its price is not public. The hydrogen target did not become a public operating receipt. The reactor's electricity did find a long-term buyer. That does not prove either project failed. It does not prove cancellation. It proves only that an old target date is not an operating receipt. So the maturity ladder looks like this. At the bottom, models and technical targets, then laboratory systems, then site integration and demonstration, then a small operating on-site low-temperature case. Above that would be an integrated commercial plant with disclosed utilization, degradation, hydrogen delivery cost, and customer payments. That top rung is the evidence the broad new build thesis still needs. Now the powering AI crossover. The hydrogen opportunity did not get worse because electrolysis stopped working. The alternative use for clean, firm electricity got better. Meta's Clinton agreement covers 20 years, and the plant's full 1,121 megawatt output beginning in 2027. Tallinn and Amazon expanded their nuclear relationship at Susquehanna through long-term power purchase agreements supporting up to 1,920 megawatts. Google and Kairos announced a multi-reactor agreement targeting a first advanced reactor by 2030 and up to 500 megawatts through 2035. Amazon invested $500 million in X Energy. The first Energy Northwest project is planned at 320 megawatts, expandable to 960, within a broader 2030s deployment strategy. Be careful with this evidence. The public announcements do not give us one universal data center power price. A development agreement is not an operating reactor. A capacity target is not delivered electricity. But together, these records establish a credible control case. Large credit buyers are willing to make long-duration commitments for clean, firm power. They do not require the reactor owner to finance an electrolyser, qualify a new molecule under a carbon rule, build storage and delivery, and find a second buyer. Hydrogen now has to beat that simplicity. This is where small modular reactors belong in the episode, as a real scenario with a real construction anchor. Ontario Power Generation is building a 300 megawatt BW-RX300 at Darlington. The project is designed to put electricity onto Ontario's grid, with the first unit targeted for service by the end of 2030. OPG disclosed a budget of 7.7 billion Canadian dollars for the first unit plus shared infrastructure. The broader plan is 4 units totaling up to 1,200 megawatts. Public investment funds later committed up to 3 billion Canadian dollars of equity. Do not divide 7.7 billion by 300 megawatts and call the result the permanent reactor cost. The disclosed scope includes infrastructure intended to support more than one unit. It is a first unit project, not a standardized 10th copy. Also, the BWRX300 is a boiling water reactor. It is not the high-temperature gas-cooled reactor shown in the most aggressive heat-assisted hydrogen concept. Darlington proves something important and more modest. Small modular nuclear is moving from PowerPoint into construction, and it still carries serious first unit capital, schedule, licensing, and public financing work. Add hydrogen, and the project stacks at least 6 risks. The reactor must finish licensing and construction. Its costs must hold. The electrolyser must hit cost, efficiency, and degradation assumptions. The 2 plants must integrate safely. A hydrogen customer must sign for enough product. Storage and delivery must work, and the incentive must still exist when a long construction schedule reaches operation. 2 technologies that exist separately do not create a de-risked integrated project. I built an editable nuclear MWH allocation calculator to make this comparison explicit. The blue cells are inputs. Every default is illustrative unless the source sheet says otherwise. This is a decision screen, not a bid model, and not an investment recommendation. The calculation covers the incremental hydrogen conversion equipment and its integration. It deliberately excludes reactor construction cost because the hydrogen and electricity cases use the same reactor. For a new build decision, first choose the higher value output, then separately underwrite whether the reactor itself can meet its cost and schedule. The existing reactor case assumes a small on-site system, 90% utilization, 50.2 kilowatt-hours per kilogram, $6 of avoided or contracted hydrogen value, low delivery cost, and a $45 per megawatt-hour electricity alternative. Under those assumptions, hydrogen netback is about $79.26 per reactor megawatt-hour. The power alternative is $45. Hydrogen wins by about $34.26. The break-even hydrogen value is about $4.28 per kilogram. That is the 9-mile point shape, high-value captive demand, and almost no merchant delivery. The new small modular reactor case assumes 100 megawatts allocated to low-temperature electrolysis, $4 hydrogen, 85% contracted volume, higher delivery and integration cost, and an $80 power alternative. Hydrogen netback falls to about $17.02 per megawatt-hour. Selling power is worth $80. The allocation gap is negative $62.98. Hydrogen would need a value of roughly $7.72 per kilogram to break even under the rest of that stack. The advanced high-temperature case gets the better electrical yield. It also carries higher equipment and integration cost, a thermal opportunity cost, and only 75% realized offtake in the illustrative case. Its hydrogen netback is negative $9.84 per electrical megawatt-hour versus $80 for power. Break-even hydrogen value is about $8.70 per kilogram. Do not turn those outputs into the headline. Nuclear hydrogen costs $8.70. Change the inputs and the answer changes. That is the point. The sensitivity table shows how demanding the new small modular case can be. Under all the other defaults, the case turns slightly positive around $5 hydrogen when power is only $30 per megawatt hour. At a $75 power alternative, it needs close to $8 hydrogen. The project is not won by an impressive efficiency percentage. It is won by a durable spread between two contracts. Policy can absolutely move this decision. It can also disappear before a new reactor arrives. In the United States, final Section 45V rules include a constrained route for electricity from qualifying existing nuclear reactors. The conditions matter. Existing nuclear hydrogen does not automatically receive the maximum credit just because the reactor is low carbon. Current IRS instructions also say a qualified clean hydrogen facility must begin construction before 2028. Refresh that rule before any investment decision, but see the schedule mismatch. A hydrogen facility waiting on many new reactor concepts may struggle to begin construction inside the current window. Canada uses a different tool. Its clean hydrogen investment tax credit is tied to life cycle carbon intensity. The published capital credit rates step down from 40% to 25 to 15 and then 0 as carbon intensity rises. Eligibility, labor rules, and equipment scope still matter. A capital credit is not the same as a guaranteed dollar per kilogram. The European Union separates renewable fuels from low-carbon hydrogen. Nuclear electricity is not renewable electricity by definition, so nuclear hydrogen is not automatically an RFNBO. But the low-carbon hydrogen methodology is a separate route. Europe bans nuclear hydrogen is too simple to be useful. China has perhaps the most interesting reactor platform. The HTR-PM at Shidawen is a commercial modular high-temperature gas-cooled reactor. Official Chinese sources discuss high-temperature process applications, including the potential for hydrogen. A 2022 regulator response recorded commercialization and economic caveats. An April 2026 Jinhua update says key iodine-sulfur thermochemical process, coupling safety and equipment work is complete, pilot demonstration research is underway, and commercial-scale demonstration work is expected around 2027. That is a different conversion route from the solid-oxide electrolysis model I showed earlier. It is progress, not a public commercial nuclear hydrogen operating receipt. The reactor is real. The hydrogen business case is still unproved. This episode keeps only the policy assumptions needed to tell the economic truth. The next and final Hydrogen Arc episode will do the full money map, eligibility, carbon intensity accounting, certification, expiry, and cross-market comparison. So put the 4 cases back on one board. Existing reactor plus captive or adjacent hydrogen, real niche. Underwrite the avoided delivered hydrogen cost, the incremental equipment, and the customer's actual consumption. Do not pretend it proves a commodity market. New small modular reactor plus a nearby industrial buyer prove the premium. I want a firm offtake contract, a credible reactor cost and schedule, and a hydrogen netback that beats the real power purchase agreement, not an assumed $0 surplus hour. Advanced high-temperature reactor plus solid-oxide electrolysis. Watch, the physics deserves attention. The project class needs a commissioned, integrated receipt showing heat draw, electrical consumption, utilization, degradation, delivered cost, and customer payment. Sell electricity, control case, underwrite the actual power contract, interconnection, capacity obligations, and buyer credit. If that check is larger and simpler, take it. What would change my call on new build nuclear hydrogen? A public project package with the reactor's actual cost and schedule, the electrolyser's operating hours and degradation, the thermal draw, the delivered hydrogen cost, a binding buyer, and a clean comparison with the electricity revenue displaced. Until then, high capacity factor is an input. The buyer decides the project. That is the nuclear hydrogen verdict. At an existing reactor, beside a customer already paying for delivered hydrogen, making the molecule can be a real bet. At a new reactor, hydrogen must pay for conversion, integration, delivery, and contract risk, and still beat a market that increasingly values clean, firm electricity. And for advanced high-temperature systems, respect the efficiency advantage without promoting a target into a plant receipt. The editable nuclear MWH allocation calculator is linked with the episode. Change the hydrogen price, power value, utilization, capital cost, delivery, heat, and policy assumptions. Then tell me in the comments, which of the 4 paths would you back? Existing captive hydrogen, a new modular reactor with a buyer, advanced heat-assisted hydrogen, or direct power sales? And what price, contract, or operating result determines your choice? We judge technologies, projects, and economics, never securities. Nothing here is investment advice. The next Bankable Hydrogen episode is the last one in the arc, the hydrogen money map. We will compare the policies and regulations that can rescore every hydrogen pathway we have covered. After that, we move to the next molecule,